is Rocio, and welcome to Physics 2212, Lab 5, Magnetic Braking with Faraday. After I introduce you to the lab and its fundamentals, I'll share with you the observational results and the computational results that I got and compare them and give you some further understanding. In this lab, we'll use an aluminum foil tube and a bar magnet to observe their interaction in both observationally and computationally, and we're going to use this all to understand Faraday's law. And we'll find that the average time for the magnet to fall through the tube is 3.32 seconds in real life versus the computational model predicting 3.432 seconds. And the magnetic dipole that it would have taken was 3.6687 ampere meters squared to match the observational time. As for Lab 5 fundamentals, in class we studied Faraday's law relating to the magnetic field changing over time and how that creates a curly E field. Its closed path integral is an equation for the induced EMF driving the current. The current gives a counteracting force, which is due to, it can be related to Newton's third law and also Lenz's law. The external field source is our bar magnet, and the induced current is driven through a tube of aluminum foil. So we'll be using the Biot-Savart law for a magnetic dipole for the magnetic field of the magnet, Faraday's law, Lenz's law, Newton's second and third laws of motion. And note that in this lab, our system consists of the aluminum tube, the bar magnet, and the magnetic force, as well as the gravitational force. So as for the observational data / results, the aluminum foil width was 0.006 meters, tube length was 0.2 meters, the radius of the inner tube was 0.015 meters, the magnetic dipole from Lab 3 is 3.72829 ampere meters squared, and the magnetic mass for the bar magnet was 0.024 kilograms. As for average experimental time, out of 5 attempts, our average was 3.32 seconds. So now I input that data into this computational model in VPython, and in this page you're going to be adding the physical constants and data to start the graph and replicate the aluminum foil tube. Here we didn't have to adjust the code, but its function is just to finish up the aluminum tube model, and at the bottom we started to put in the bar magnet by putting its mass and the magnetic dipole. We fixed up the code to finish the bar magnet, and now our objects are in there and ready to be put to work. We set our initial conditions, so time equals 0 and the position is at 0, and we calculated the magnetic field of the bar magnet using the Biot-Savart law. The reason why we were using the Biot-Savart law is because this magnet is moving, and now in this code we'll calculate our magnetic flux due to the falling magnet. Remember, speed is the magnitude of velocity, and we just split up the formula a little bit so it would be easier to type in. Then I fixed the rate on how fast the magnet will be falling down the tube to be 500 so that you can see the simulation a little bit better, and we can calculate the current in the ring as the negative derivative of magnetic flux over the radius of the ring. Then we computed the magnetic field at each ring and calculated the magnetic force on the ring and on the magnet, and as we stated at the beginning, the net force is the magnetic force and gravity. So here's the magnetic dipole, our bar magnet, falling through the aluminum tube, and up next, right next to it is the velocity versus time chart, and you can see that it took 3.432 seconds for the magnet to fall down the tube, which is very similar to our observational model. And yeah, it's really similar because the percent error is 3.37%, and my measuring could have been slightly off, or my time could have been a little bit inaccurate. And also keep in mind our experiment was not done within a closed system, so external forces would result to incorrect values. And then for further understanding, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, The forces pushing up on the magnet would keep increasing until the magnet stopped from falling through the tube completely. And what if holes or slots were cut into the tube? How could this affect the ring currents in your model? The model would be affected by the tube's magnetic field on the magnet, and that would in turn affect the force and decrease the time it took for the magnet to fall through. Thank you.